comes about in differential equations, which we have talked about on this channel before, are called Laplace transforms. Now there are many different types of transformations that you can do with integrals. Integral transformations have been studied for a couple hundred years anyway, and have been found to cause certain integrals which we thought were impossible are actually not that bad once you do this weird transformation thing. It isn't always weird, but many times it is. So Laplace transforms in particular are usually written as this cursive L of f of t is going to be equal to the integral from 0 to infinity of f of t times e to the negative ts, I think, right? Or st. Doesn't really matter there. Where s is just some constant, but then we evaluate this on, of course, negative st f of t dt. Yeah. Which is going to give us a capital F of s. So the individual functions that we get for this kind of stuff really are not that much fun depending on what you're doing. Most of the time they require integration by parts. Many of the times it gets really ugly and really nasty when you're trying to do these kinds of integrals. There we go. So for instance, the Laplace transform of just t is going to be the integral from 0 to infinity of t times e to the negative st dt, which again, we're going to be doing integration by parts on this. You can't do u substitutions or anything like that. It's just not going to work. So here we let u be equal to t, and therefore du equals dt. dv is going to be equal to e to the negative st dt. So therefore v is going to be equal to, you take this integral, take the integral of this thing, s is a constant, so this is going to be a negative 1 over s, gets knocked out front, and then you've got e to the negative st. When doing integration by parts, again, this is uv, so u is just t, v is this thing, so negative 1 over s times t, e to the negative st is uv, minus integral of v du, so v is a negative 1 over s e to the negative st, times du is just dt. And then do this integral, which looks oddly familiar, doesn't it? This is going to be a negative 1 over s t e to the negative st, evaluated from 0 to infinity. 0 to infinity. And this is a positive 1 over s times the integral of e to the negative st dt, which we already did on the step above. The integral itself is just going to be the thing we found, well, the v that we found earlier. So this is going to be a negative 1 over s t e to negative st, evaluated from 0 to infinity. Again, t equals plus 1 over s times a negative 1 over s e to the negative st, evaluated from 0 to infinity. So what's that going to be? Well, you can plug in infinity into all of these individual pieces. Again, we can't technically do it, but you just say that, okay, I'm going to take the limit as b goes to infinity of negative 1 over s times b e to the negative sb. All right, in this particular case, you have to look at what's known as the hierarchy of functions and say, well, which one's going to happen faster? Is b going to go into, is a linear b, this term here, going to go off to infinity, or is e to the negative sb, is this b going to cause the e to do something faster? And the answer is, well, of course, exponentials pretty much always win. So certainly over a linear function. So here when we plug in larger and larger numbers for b, having an e to the negative sb is going to get us smaller and smaller and smaller values. It's going to tail off as we continue on further. So here, this is going to just end up being 0. All right, then we subtract this thing evaluated with 0. So now this is going to be a minus a negative is a plus. 1 over s times 0 e to the 0. All right, well, that's easy. This whole thing is now just going to be 0. Plus. Oh, nope. Minus. All right, we end up with this piece here. We have 1 over s times a negative 1 over s is a negative 1 over s squared. E to the negative st, evaluated from 0 to infinity, which is again going to be negative plug in all right, so a minus 1 over s squared e to the negative s, and again this is going to end up being b, so we want the, screwed that up, didn't I? Not a big deal, just kind of forgot to put the limit in there. B goes to infinity of 1 over s squared e to the negative sb, and then we're going to again subtract, which makes this a positive. We're going to plug in 0 for t. This makes 1 over s squared e to the negative, well, again, that's just 0, e to the 0. E to the 0 is just 1. And this time we don't have a term out in front that's causing it to be 0. We don't have a t. We just have this constant, 1 over s squared. All right, so again, exponential is running towards 0 in this particular case. As b goes to infinity, e to the negative sb is going to become e to the negative infinity. Well, e to the negative infinity, again, causes this to go off to 0. So 0 minus 0 is still 0. 0 plus 1 over s squared is just going to be 1 over s squared. So f of s for the original function, Laplace of t, is going to be 1 over s squared. All right, there's a whole table of these things in your differential equations book, those of you who have one. And if you don't worry, it's coming. All right, so that is a Laplace transform. It is a specific use version of an integral transform. So basically what we're doing is we're taking the integral, usually from 0 to infinity, of some function times what's called a kernel. So this little e to the negative st is the kernel of the particular transformation we're talking about. So generally speaking, this is an integral from 0 to infinity of f of t times some kernel, which is a function of s dt. Now it is also possible that the kernel has a t in it, so we can actually change this a little bit and say it's s comma t dt like that. All right, something else that they want to do in the book is to compare two different types of integrals. So for instance, taking the integral from 1 to infinity of a function dx over square root of x plus 1 isn't actually possible to take this integral. So we would need some sort of dx term up top to be able to compare it. And we're only off by a half of an exponent instead of one full exponent. So that's unfortunate. What we can do is, instead of actually taking this, we're going to compare taking the integral from 1 to infinity of dx over square root of x. Adding a 1 on the outside here is just going to increase the denominator and actually make the whole function just a little bit smaller. So here what we get is that we're actually looking at a function which is slightly larger than the original one that we wanted here. And if we look at this, this is going to get us let's see, that's going to be a 1 over positive a half. Because we had an x to the negative 1 half, we're going to increase that value by 1, and it's going to end up being positive 1 half. So 1 over 1 half times just the square root of x. Evaluated from 1 to infinity. here we get a 2 square root of x evaluated from 1 to infinity, and then we can alter this again so that we get the limit as b goes to infinity of 2 square roots of b minus 2 square root 1, which in this case, right, square root of 1 is just 1. We get minus 2 at the end. And then here, this is going to be limit b goes to infinity of 2 square roots of b. Since we're taking the square root of something that's going off to infinity, we're still going to get something infinite in extent. So this is still going to be infinity, minus 2 is just going to be infinity. So this will diverge. However, this thing here is smaller than the original. How much smaller? Well, not by a whole lot, because the denominator is just going to be plus 1. However, we can't actually prove that the original one here will converge or diverge. We just know that it could diverge because our comparison integral ended up diverging. So because the comparison integral diverged, the function underneath it could diverge or it could converge. We don't know. So in order to obviate that, we have to, or in order to fix the fact that we have multiple answers here, or multiple potentialities, we haven't eliminated any, we have to change the comparison integral. Right, since this integral diverges, it is going to be inconclusive to tell us what's going to happen with the original. So we have to figure out something else that is better, and in this particular case, if we can find a function that will get, instead of over the top of dx over square root of x plus 1, if we can get something that is underneath it, which then also diverges, then that proves that the thing above it must diverge, right? If something underneath a particular function, like down here, says that it will diverge, then it is not possible for something that is always above it to be able to converge. There's no possible way. So in this case, what's going to be easy that we can do to find something out? Actually, I didn't need to cross all this out. We could have taken the integral of 1, or from 1 to infinity, of dx over 2 square roots of x. 1 over 2 square roots of x will always be smaller than 1 over root x plus 1, at least from 1 to infinity. Right, so for all values that we're going to get, this ends up just being the exact same integral, but it's half of what we found. So I didn't really need to cross all this stuff out. So we would get the limit as b goes to infinity of the square root of b minus 1. Which, yet again, the limit as b goes to infinity of the square root of b is still infinity, and then we subtract 1, so it's still infinity. So in this particular case, this still diverges. However, coupled with this fact that we found earlier, allows us to say that since something that is always below it diverges, then the integral from 1 to infinity of dx over square root of x plus 1 will also diverge. It's a fun little puzzle to try and figure this stuff out. Next section starts looking into all of the individual series tests for Calc 2. Be honest with you, I don't want to do them tonight. I kind of want to just do some like random stuff. But at the same time, I don't know if that's going to yield any results whatsoever. So it's like, I don't want to scare away all of the people who are here for video on demand. See you out there. Thank you. I mean, I was just sort of talking about it. So. Oops. All right. Something more my speed for tonight, because I don't know. I'm just not feeling like I want to do the other one. So in Calc 1, let's do substitution for integrals. So we had something, well, I mean, we could do just about anything, but in the case of substitution for integrals, we can throw in pretty much anything we want here. So take the integral of x times the quantity 1 minus x raised to the 56th power dx. So for this, naturally, just looking at it, you'd be like, well, I can't do that because we got multiple pieces that are not really communicating terribly well. If we let the inside of this be u, then du would be the derivative of 1 minus x, which would just be negative dx. Now, unfortunately, we do have this other x that's out here, so that isn't being included in all of this stuff. It's going to be much harder to try to figure out what exactly is going on here. You could let that be, solve it for this. So x would end up being equal to 1 minus u. And in theory, you could start trying to combine that, but it's going to get complicated. So instead, one of the things that you can do is, instead of doing a u substitution like that, we can split this up. And say that since we're multiplying here... Wow, I just did that, didn't I? Okay, nope, never mind. Let u equal 1 minus x. Yeah, I tried to like give each of those pieces a 56th power. That does not work. All right. Yeah, and instead of multiplying this all out, as much as I do love Pascal's triangle, this is going to be a nightmare to try to do with the 56th degree. You're going to have 57 terms going across. So yeah, let's not do that. On the other hand, if we let u be equal to 1 minus x, then x is equal to, if we flip this around, 1 minus u. We'll use that here and use that here. So what we've got is the integral of parentheses 1 minus u times u to the 56th power du. Because, again, dx is just du. Oh, no, negative.